Okay, guys, in this helpful hint video, I'm going to do two of the FRQs with you guys. I'm going to do the one on page 60, and I'm also going to do the one on page 68. The rest, though, I'm going to let you guys do because they're pretty much the same thing, okay? So this is the one on our page 68 of our blue books. Let's take a look at it. We're talking about a hot air balloon, and this hot air balloon is expanding. And then we're looking at a time frame of going from 0 to 12 minutes. It tells us that the graph is concave down. That's actually going to be helpful later on in our question. So our table up here tells us two things. Tells us at what time the rate of change is going, what the value of the rate of change is. So there it is. Now, so what's important to understand is that this is the rate of change, this is feet per minute. So that means at 0 minutes, the balloon is expanding at a rate of 5.7 feet per minute. At 2 minutes, the balloon is expanding at a rate of, the balloon's radius is expanding at a rate of 4 feet per minute. So it's important to understand what that represents. So let's go ahead and begin. So the first thing I want to focus on is, let's take a look at C first, right? It says use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate this. In other words, the area under the curve. Now there's a part that we haven't talked about in class yet, but it's not that hard, and I figure, okay, well, let's go ahead and at least break some ground here. We're definitely going to talk about this stuff later in class, but using correct units, explain the meaning of that. We don't know how to do that yet, but I'll show you. It's actually pretty simple. But main thing I want to make sure you guys can do here is this green part for now. So let's focus on that. So we want to do a right Riemann sum. Now it says 5 subintervals. Now don't let that deceive you. Don't think, okay, I got to subtract my smallest one from my biggest one and divide this up into 5 equal intervals. Because if you do that, it's not gonna work out for you because these are not evenly spaced intervals. Okay, so it's not going to work out. The only time you need to do that is if it says you need 5 equal subintervals, but it doesn't say 5 equal. So here's the deal. Your subintervals are exactly what they've given you in the table. Here's one, here's another one, here's another one, here's another one, here's another one. There's your 5 subintervals. So I know that the way they're using their language is a little different than how I'm using mine, but there it is. So I'm using a right Riemann sum. We have 5 subintervals, or in other words, 5 rectangles, I mean. And the base of this one is 2. The base of the next rectangle is 3, 2, 4, and 2. And we're doing a right Riemann sum. The numbers on the right represent your heights. So this is the height of my rectangle on the right. This is the height of the next one, and so on, until you get to this one here. We don't include the height of the last one, right? And so what we're going to do here is we're just going to go ahead and multiply these heights by these bases up here, and we have our answer, okay? So what we would do then is we would say that the area under that curve is approximately equal to, this would be 8 plus 6 plus 2.4 plus, would that be 2.4 as well, I believe, plus 1. And, you could add them together if you want to, but remember, use your freedom wisely. This is an FRQ. I don't have to simplify that. That's the answer. All right. Now it says, using the correct units, explain the meaning of this integral. So I'm going to explain something to you guys first, and then I'll come back to the question. So let me explain something to you guys real quick. Let me switch slides here. So whenever you have something like, let's talk about position, right? We had a position function earlier this year. When you take the derivative, well, the position function, let's say it's something that's measured in something like meters, right? Those are the units, we'll say. Well, when you take the derivative of this thing with respect to time, that's like you're dividing the distance by time. And so that becomes meters per second, right? And we also talked about how we take the second derivative, that's your acceleration, and that's meters per second, or per second squared, right? So we talked about that. But something we haven't talked about, though, is what this question's asking, but it's actually asking the same thing but going backwards. So in other words, what are the units for the second derivative position? It's meters per second squared. What do you get if you integrate s double prime with respect to t? Well, that just gets you here. So it goes from being seconds squared to being just seconds. And what happens if you integrate this derivative with respect to time? It goes from being meters per second to just being meters. So what I want you guys to notice is that whatever variable you're integrating with respect to, you're going to remove that variable from the denominator. So we're integrating with respect to time, so we're going to lose 1 second if we integrate. And we lose a second again if we integrate here. So now let's go back to this problem here that we're looking at. They're asking you, what are the units for this expression here, r prime of t dt, right? What are the units for this expression here? Well, r prime of t is feet per minute, right? But since I'm integrating it with respect to time, we lose the minutes, and the answer that we get, whatever that is actually just feet. So when you integrate a rate, you lose the time, one of the time factors in the denominator, and you end up with whatever's left. In this case, it's just feet. So this answer, whatever the answer is, it's feet. Now we'll talk more about that later, and it'll hopefully help you make a little bit more sense of it. But it's not too bad, and it kind of connects nicely to something we've already learned. So I feel like it's worth talking about. All right, so let's go ahead and take a look at the next part here. Part D says, is your approximation in part C greater than or less than, and give a reason for your answer. Okay, so what they're asking you is this an overestimate or an underestimate? That's an important question. All right. Well, I gave you guys a chart earlier in this chapter. If your function is increasing or decreasing, that's something that has to be considered. And something else that has to be considered is just whether you're doing a right-hand sum or a left-hand sum. Okay? Now, if your function's increasing and you're doing a right-handed sum, it's an overestimate. If your function's decreasing and you do a right-handed sum, it's an underestimate. If your function is increasing and you're doing a left-handed sum, it's an underestimate. And if your function is decreasing and you're doing a left-handed sum, it's an overestimate. Okay? So, what's happening with our function here? Well, I thought this would have something to do with the answer, but it actually doesn't, so I'm going to leave that out. That actually doesn't have anything to do with concavity. It has to do with increasing or decreasing. Well, first of all, take a look at your function here. Would you say this function is increasing or decreasing? You see the numbers are going down, 5.7, 4, 2, 1.2, 0.6, 0.5. So it's decreasing. And we're doing a right-hand sum. That means our answer must be an underestimate. Our rectangles would be below the curve. So the answer is it's an underestimate, but you got to make sure you write it correctly. So how you would answer that is you would say it's an underestimate since r prime of t is decreasing. Now, to be more specific, you might want to say it's decreasing on the entire interval because that matters, right? That's the interval we're looking at. So it has to be decreasing on the whole interval. If it wasn't decreasing on the whole interval, then it wouldn't be strictly an underestimate. So it's decreasing on the interval from 0 to 12, and we are using a right-hand Riemann sum. You could just say right-hand sum, I think is fine. So there you go. You have to say, I would say that three things are important. Decreasing, interval, right-hand sum is how you're going to answer that question completely. All right, next question. So I included this question not because it's relevant to what we're learning right now. This is the one on page 68, I believe. I'm including this question not because it's relevant to what we're learning right now, but because it looks like what we're learning right now, and it's actually different. So I want you guys to notice a little bit of a difference here. With the last question we looked at, we were finding an integral of a derivative, right? We were finding, what was it? It was integral of r prime of t dt. And that's also what was in our table. When we looked up at the top, we had r prime of t in there, okay? In this case, though, this is a different question. What I want you guys to notice for this question is they want us to find the integral of h prime of t with respect to t from 0 to 10, but this is not h prime of t, right? That's h. That's a different question, okay? So we're going to handle this question very differently. Now this one up here, you could handle this one in a similar fashion as the last question, but this is different. So the way that we're going to handle this is we're actually going to integrate it. What is the integral of h prime of t with respect to t? Well, it's h of t, right? When you integrate a derivative, you just get the original function. So the integral of h prime of t is h of t, right? But this is a definite integral, so when you have a definite integral, what you're going to do is you're going to take the integral, which is h of t, and you're going to plug in the upper limit, and you're going to subtract from it. The same thing with the lower limit. And those numbers are actually right in your table. H of 10 is 43, and h of 0 is 66. And if we go ahead and subtract those, what do we end up with here? Well, I guess it's an FRQ, so we can actually just read it. Then they want us to explain the meaning of that expression in the context of that problem. So remember, when you have an explanation or trying to interpret an answer, you should have your input units, you should have your output units, and you should also have the context included in your explanation. So what I'm plugging in, my input units, is minutes. What I'm getting out is an h value, right? So we're getting out degrees Celsius. And the context here is basically we're talking about a pot of tea that's cooling over time. Okay? So let's go ahead and interpret that. What this answer means, I think I'll go ahead and I'll do the 43 minus 66. I'll just help my answer make more sense. Negative 23. Okay. So what this means is that the temperature of the tea on the interval, which is going from 0 to 10, decreases by 23 degrees Celsius, and that'll do it. So here's our input units, 0 to 10 minutes, because we could actually write minutes here. Here's our output units, and then the context is about the temperature decreasing. And the reason I say it's decreasing is because It's negative. Our answer is negative. Move it down. So there you have it.